Okay, so thanks. Welcome to the second day of this GYAN course. I think Professor Das will make this announcement, but we are thinking to have the time slot between 10:30 until 11:15 for open for discussion. So I'll stay in the room, and then I would welcome people that are interested in discussing further some of the things from the former lectures to just stay on. It's informal, okay, so we just I'll just take questions as they come, and yeah, it's just for those that are interested. The others can basically take the longer break, and we still have an half an hour break for everybody from 10 to 10:30. Okay, so after the tea break, then who is interested can come here, and then we can discuss. Okay, and again, you can send me emails, and if you see me around, then we don't need any appointment. We can just talk. Okay. I don't know if there is any question or something you wanted me to clarify from yesterday. We are still kind of in a general introductory phase, so probably we'll have more questions when we go deeper into the technical subjects, but asking just in case. Okay, so seems not. So I think we reached here yesterday. So today I'm going to do mainly two things. I'm going to finish this introductory part of 5G, okay, and the rationale and the scenarios, the general requirements, okay, and today I'm also going to introduce the technology components that are pretty much part of the 5G story, either in the standard already or considered for future adoption. And then in the afternoon, my plan is to start with the second module, so we dive deeper into the technical subject. So I'm going to basically introduce the concept of MIMO. Probably most of you are familiar with it, but I still think it's a good idea to revise the basics, and then because we are going to see quite a bit of MIMO in this course as one of the main components of 5G, especially massive MIMO. Okay, so good. So I mean, we already went through this kind of story, right, where you have many more applications than we are used to from 3G and 4G, for example. So especially machine to machine or machine type communication or IoT, they're all kind of synonyms, telling that essentially you have machines in the loop now communicating, and once you remove the people from the equation, of course you have more degrees of freedom, right, because you can literally blanket any environment, even hazardous possibly, with communication devices. Okay, so that means, for example, things like automotive, smart cities, agriculture. I mean, probably in India is the same. In where I live in Ireland, agriculture is a big thing. So they have actually research centers talking about how you can track basically animals, and for example, if a sheep goes astray, then to find the animal and stuff like that. They even have a center. It's called Future Milk. I don't know exactly what they do, but they have a lot of this IoT for agriculture applications. So other interesting things they are doing. For example, I heard there is a problem of fires. I mean, not as much as in India probably, because we don't have so much sunshine, but it could happen, right, that for example if you have a stack of hay, it might get you might get a spark, and maybe it can be that the whole barn is on fire, right? So these things happen, unfortunately. So they do have simple things, like they have a humidity or I think temperature sensor, something like that, and then if there is something that is crossing a critical threshold, they simply communicate to a Wi-Fi access point, and then the farmer immediately can take action. Or there are other things, for example, when the cow has to be milked. Okay, so you see there are actually a lot of applications in agriculture, for example, and asset tracking. So you name it. Now there is this last picture which is on purpose with suspension dots, because these things I think are coming. I kind of mentioned it yesterday, like the service robots, and I'm not a robotic expert myself. I just took 2 modules in control theory, as most of the people in this class, probably my EE studies, but I do talk with people that are from an automation, robotics, control background, and according to them, these things are coming. Okay, so you would have, I mean, maybe this is a bit futuristic, but you would have totally assistants, okay, that are robots. So that's yet another application of you know, future communication systems, because of course, you know, if you imagine you have to communicate with a sensor, the more so you will have to do with a robot, right, which is something more intelligent, more capable. So these things are, I think in the next decade we are going to start to see it around us. Okay. Yeah, so basically again, there are many classifications you can do about the technologies, right, and the standards. One way, for example, is to plot, I mean, to kind of position the standards against range or data rate. So, for example, cellular is kind of closer to the top right of this chart because it tries to target both, right? You want high data rate and you want good coverage, pretty much. That has always been the case, okay? The more so with 5G, but it's always been the story. And then Wi-Fi, it's more, let's say the 802.11 standards, they are more like biased toward data rate, right? And less about coverage. I mean, there was some chats a few years ago, I don't know where that went. For example, in Singapore, they were talking about the super Wi-Fi, which was basically targeting the usage of bandwidth bands sub 800 megahertz, like these TV white spaces, right? And they were thinking of having this you know, license-free system covering, which would be fantastic, I think. Imagine if you could have Wi-Fi everywhere, right? That would be great. But I just didn't see that, you know, widespread. I think there is a problem with bands. You could do it, of course, technically, but you see, these TV white spaces in the beginning, they were meant to be for mostly unlicensed use, on, you know, free of charge, so to speak. You don't need a license, but I think LTE operators were quick on securing them. So we started to see, you know, the carriers to actually to act on buying these bands because they're very good. Okay, they're kind of covering large distances with little power. That's why TV stations or radio stations use them, right? So again, you know, the range has to do with the carrier, right? The frequency you can secure. The IoT standards. Now there are a few. I'm not so much an expert. I kind of, you know, starts to understand that world because I was totally just a cellular person up until 2 years ago, and then the IoT, you know, stormed into the room, so we had to adapt. Okay, so now a lot of the projects we do have to do with wireless sensor networks, IoT, and stuff like that. They have a few standards, so Sigfox, LoRa, weightless. They are kind of there. Seems to me Sigfox and LoRa are kind of, you know, the dominant ones at the moment. NB-IoT is kind of the LTE trying to cope with that. So it's called narrowband IoT. So what they did, they have these essentially they have different categories of user equipment in LTE, and you know, depending on the capability, they give a number. So, for example, category 1, 2, 3. So, the higher the number, the more advanced the capability of the phone. For example, in terms of duplexing and, you know, and carrier aggregation capabilities. But they also have a version that goes opposite. So normally the numbers in LTE go up because the technology progresses. But with IoT, they went backward. So they have a category 0, as far as I know, which is kind of very simple, you know, phones or devices targeting IoT. I still think they're a bit too complicated for some IoT applications, but so LTE is aware, okay, of this new use case, and they're acting on that. They are normally targeting range rather than data rate. So normally IoT applications are not about sending a lot of information, normally, but you do have some IoT applications that do that. For example, the cameras, or when you have rescue parties, they might have to stream live, right, the situation. Or also I'm thinking like military applications. I think if you could get like a video, right, live footage, that's very good. So you do have things that are a bit on the data rate side, but normally IoT is really about a small amount of information to be sent in an intermittent way. And it's very asymmetric. So for example, normally cellular communications are very asymmetric on the downlink side. You definitely download more than you upload, okay? IoT is reversed. It's definitely much more on the uplink side. The downlink is more about controlling, maybe, okay, ping in, okay, tell me what you have, it's kind of, okay. But then the real information transfer happens in uplink, right? The sensors are sending information to a gateway, to a sink. So there are some differences between the two, and then you have systems like 11AH, which is this new millimeter wave, I think, system, okay, targeting, as far as I'm aware. AY is another evolution, so they are basically like Wi-Fi using the 60 gigahertz band, which provides very high data rate with some problems though that come with using a high carrier frequency. We are going back to this, okay. So again, you know, same story, just a bit more detail. So you do have things like, you know, smart metering, disconnected herd I talked about. I mean, in the Trinity College campus, I see this kind of things like the connected trash cans. So they're trying to optimize the disposal probably of trash. So when it's filled up, I think they send a signal to somebody, something like that. Okay, so yeah, surveillance cams have been there for a while, and now, you know, always consider that for some, you see, the thing about IoT that changes the picture is that you have an immense amount of data being collected. It's not so much true, I think, well, you might have that too for cellular systems, but definitely IoT is about collecting a lot of information over maybe a broad area. Now, raw data might not tell you much until you process it. That's why AI and, you know, all of these big data, data science activities are kind of really exploding at the moment. So, because, you know, it's not by chance that you start to see a lot of interest in these techniques. They've been there for a while, but now you do have a use case that is really suited for, you know, suitable for them. So once you start to see patterns and to, you know, kind of discover meaning in the data, then you can do better things. For example, one thing you could do, I'm thinking again, going back to this example of the airplanes we had yesterday, there are some things, so normally we do optimize engineering systems based on average conditions, right? Which is fine. But what happens if there is a rare event which is potentially disastrous? For example, normally planes do not break down normally, but yet they do. So the idea behind, for example, some of these applications with big data and IoT, once you collect all of this information, there is something called rare event prediction theory. So you could, for example, find out that maybe you are close to something that is dangerous, okay? You wouldn't see it unless you do some processing, filtering, you know, and so on. I'm not an expert in that area. I know people that are, okay, I talk with them, and there are actually AI techniques, filtering techniques, data processing techniques that can help you. Of course, there is probably no guarantee that you might catch all the rare events, but you start to be more sensitive to those. So, and that's very good, because you might have actually, it could be for you know, industrial control. You know, sometimes it might be, yes, sorry? Oh yes, I think, you know, rare events essentially, yeah, it's like events, you know, that are not normally happening, but when they do, so you want really to minimize all possible outages. So we go back to the discussion I had about this critical IoT, right, yesterday. So we are not just happy now with things working fine most of the time. We want them to work fine all the time, possibly, okay? And so it's again about, so there are some people talking about the importance of the tail in distributions, okay? So it's not just enough that you focus on the big, let's say, on the values of the probability density function of any phenomenon, which are big. You also want to check what happens on the tail side, because some distributions are called fat tail, and so they're not negligible, those values. Okay, they're small, but not so small. So there is, you know, there is this kind of critical IoT people that are focusing on these things, and I think rare events, minimizing outage as much as possible, very hard quality of service requirements that have to be met with certainty. So all of these are kind of part of one story, I think. So many things are happening in this domain. Another big thing that is coming up, it's been there again for a while because there have been standards like, I think, if I'm not wrong, 11P was about that, this vehicular communication. But now I think it's coming up stronger than before. And you do have things like the 5G Automation Association, which is kind of, you know, the 5G, I mean, let's say the automation industry looking toward 5G, so they kind of, you know, associate, and you have big companies like, for example, Jaguar, you know, all the big car manufacturers are now, they definitely have some work going on in communication. Okay, so they want to have vehicle to vehicle, for example, for self-driving cars. That's important, right? It might be for safety. You might want to just avoid hitting a pedestrian or a bike, right? So, and sometimes you have blind spots, right? So, for example, you might even have, you could even have a sensor telling you if somebody is coming, but maybe at that point there is something blocking. So they are thinking about multi-hop to convey this message. So the usual things we do, but with a different target now, right? Which is traffic safety and you know, optimization. I did myself a bit of work, you know, in IoT for traffic management. I mean, road traffic management, and you do have, you know, quite a lot of problems to do with medium access control. So we do have communication problems. Just that now the ultimate metric is not the throughput per se. So we don't care so much about that, but we want, for example, to minimize accidents. We want to minimize the time a car has to wait at the traffic light, because that's time wasted, right? So you see, these things are more important now. So in essence, the communication is not the end goal per se, it's more the means to achieve another goal. I don't think communication is going away, it's just, we are just kind of shifting the focus, okay? Yeah, so we're not really going to do too much here. I actually have a paper that just got accepted to a conference with Professor Suvra, and we are working on vehicular ad hoc networks as an application. Well, if you want, we can actually, you know, grant you access to that work. I'm not going to cover that in this course, but yeah, we do have something there. And definitely in my research center in Ireland, there is a big group actually working on this. They do have things also. You see, vehicle doesn't mean terrestrial, by the way. You have a huge, again, I'm not covering this in this course, a big part of the 5G story starts to be about drones, UAV, unmanned air vehicles, right, aerial vehicles, and there are a lot of new problems. For example, we don't have even very consolidated channel models for that. It's a new story, okay, because you do have, first of all, you have you have variable heights. Now it's kind of easy in a sense because the users are always at a certain height, more or less, and the base stations are always at a certain height. With drones, that could change both ways. You could have drones acting as a user or drones acting as a base station, as a relay. Now, you could ask, why the heck do we have to do that? Well, there are problems because battery is an issue, safety is an issue. If a drone drops on something, it might be dangerous, right, or somebody even worse. On the other hand, though, you have advantages. What is the advantage? The advantage is the usual one, why you have what I was saying yesterday about, you know, uplink and downlink, that you need to place things so that you have a clear view. Same thing with drones. You could actually be much more flexible and find out line of sight all the time. Not with complicated signal processing, but literally just checking, okay, at this point maybe I'm clear, fine, no interference, right? No path loss in a sense, but you do have it, as it works in your favor, it works also against you, because as you do it, other cells might also do it, so it's a lot of interference coming up now, right? Interference of a bad kind, because they are all line of sight. So what I'm saying is, like, you see, if you start to have all of these drones above, you know, the skyline of a city, you have a very strong signal toward your user, but so you have very strong signals coming from interferers, which is not normally the case in the communication we do right now, because normally you are the only one in line of sight. and then the interference maybe are coming from a non-line of sight path, right? So these things are happening. I'm working on a project with Nokia. They're very interested in this. They did I think they got an award for best demo with an helicopter in Globecom last year, if I'm not wrong. So definitely it's a topic that is coming up, and in my opinion, you know, part of the goal of this course is also to seed some plants, some research ideas. So if this is a good topic for a PhD, I think, because it's something that is coming up strongly. Okay. Tactile Internet has been there for a while, so I just wanted to put it there because, you know, it's part of the story. So I mean, this is more to motivate where we got this kind of 1 millisecond delay that we mentioned yesterday in critical IoT, or, you know, ultra reliable and low latency communication. So it has to do with the with the senses of a person. So when we interact with the keyboard, essentially it's manual and visual. It's about 1 second reaction time, okay, between the time you let's say you get an input and you process it. Audio is faster, 1 order of magnitude. Visual is yet faster, another order of magnitude, but the faster of them all is tactile, right? If you burn yourself on the stove, it takes this kind of time to retract your hand. You wouldn't linger there, right? And that's because, or when you're hurt, right? When you get a sting, right, from a bee, you get you know, some pain. That's because it's like the tactile sense is the fastest one. Okay, and there is a reason, I think. Anybody that knows what this figure is? Who drew that? Any guess? Da Vinci, very good. It's kind of the perfect proportion of human body, kind of, right? Okay. Okay, so essentially that's why. Now the problem is, fine, it's easy to say. How do we get there though? Because right now, so let's say in 4G we are talking 50 millisecond delay, and we are happy with that. Maybe, you know, LTE beyond, advanced, we were talking 10 millisecond. But now it's, you know, lower, another order of magnitude. Now the problem is, speed of light cannot be overcome, right? So as far as we know, the time it takes to travel 30 kilometers, which is not an insane distance. For example, if you have to monitor a field, right, or a certain area, it could be a reasonable distance, right? To go both ways is 15 kilometers. Actually, is not such a huge distance. Like a city like Calcutta, probably be beyond that, right? And that takes 0.1 milliseconds. So it's already 10% of the budget just due to the fact that light has to travel. On that you have to add, you know, all of the things to do with control, synchronization, taking a decision, processing itself. It's not just about the network bit, right? Once you get the samples, you need to do some work, right? So all of this eats up the time budget. So people have been thinking what to do. So of course you can do things like at the network level, optimizing protocols, routing. You might actually have fast hardware. So they're working on, I think I'm thinking of Dresden in Germany. They have something on that. So they are basically doing 3D beamforming at the nanoscale. So they do have memories essentially to basically make much faster the processing. So they literally have like, you know, like nano beamformers speeding up things. Okay, they are doing this kind of nano communication. And what I said yesterday, flexible numerology, so changing the frame, the time transmission interval to make it more, you know, reactive to changes. So these things, I think, it's not mentioned here. I think a big part of it is also AI, predicting things. If you can decide in advance, it's faster than anything else. Okay, you're literally waiting just to deliver the content. Of course, that relies on the assumption that things can be predicted. Okay, that there is some regularity in patterns, but if there is, there's nothing faster than that, because you don't even have to do processing or conveying information. Information is already there once it's stored, right? Okay, so that does it for the let's say scenarios. So what I'm going to talk about now is a bit about the technology components. Any questions, comment? Yes.
So in AI to work, we need the training period. So you have to
For what to work, sorry?
Artificial intelligence.
Yes.
So we have to train the system.
Yes, I tell you the bit I know, which is not much because I'm not an AI guy. I know people that are definitely super smart in that in Dublin, and if you have questions of that kind, I'm happy to relay them. What I know, you're right, okay? I think you're right, so you need to train. For that you need good data also, or meaningful. Now, a friend of mine who has been working all of her career in machine learning, AI, and applications, okay? She told me, look, it's kind of funny to see all of these works popping up, and they kind of work, they're working on the assumption of a fake model. What do I mean? They do things that are theoretical, simulation-based, and they say, okay, you have to somehow to model your system first. So maybe you say, okay, I have a Gaussian assumption. And then they put learning on top, and guess what? The learning tool discovers what you already know, right? You see, it's not a real problem. So if you really want to benefit, to reap the benefits of AI, you need to have data that you don't really know much of in the first place. You collect them, and the whole point of learning of data is of data science is to discover things. So I mean, again, I'm not an expert. I'm just relaying the opinion of an expert. Be very careful about reading stuff when they don't tell you anything about the data, or it's not data actually collected, because it's kind of a fake problem. It's math for the sake of it. That's not the point, okay? That if you have data, yes, and then training is there, true, but possibly you don't have to train all the time. I think you have to train in the beginning, and then once the machine is trained, unless there are sensible changes in the data set, you can actually rely on these predictions. And I think there are also techniques to speed up the training probably, but I think you're absolutely right. You have training, and that goes against real time. That's why I think these are things that you do offline, and then hopefully you use instantaneously. I don't think you could do caching and training at the same time. You have to alternate probably. First you have to learn where to put things, where to deliver the content, and then you use it. And then of course if you start to see it doesn't work, there are actually things you can do in machine learning to tweak things, right? There are parameters you can tweak. So we did actually a project which is not part of this course. I supervised the communication part, but there was a group supervising let's say the molecular communication part, and we did apply machine learning to discover topologies in the brain. So again, preliminary and so on, but we have some work in that going on. And so what we did was actually, we are writing a paper on that. We did apply network tomography as a concept. So tomography is something that has been there for internet, where you kind of try to infer the topology based on inputs and outputs, kind of a black box thing, but you want somehow to discover the path, and that could be useful for brain too. Okay, so to discover how the signals travel through the neurons. Now, so far we managed with only few neurons, and we found, for example, the star topology is very popular, apparently. It's kind of something that appears quite a lot. There are speculations when you go to bigger scale, like the brain scale, real scale, that it could be small world topologies, which have been found in many other systems. Okay, small world means you have like some hubs that a few nodes are very connected and many others are not so connected. So these things are there. So machine learning has been applied there too. So machine learning has been applied everywhere. I think again the discriminant is whether you really need it or not. And if you need it, it must be that you have data available, or you have to find it. Otherwise, I think if you are doing a PhD or some work without using real data, you would immediately get a big criticism at the time of your either publication submission or PhD defense or whatever else, because this is something that is important. Okay, but AI is coming. AI is definitely, I'm not even saying it's the future because it's already the present. So I think probably what I could see as a big game changer in the next 5 to 10 years is probably robotics of any kind. That is kind of the future. Let's say near to mid term future. The present is AI. It's already there. Okay. So it's definitely something worth studying. To give you an example in terms of teaching, so when we teach our subjects in 4th and 5th year in telecom, Well, depending on the course, you might get, say, 10 to 30 students taking them. We ran for the first time, not me, a colleague of mine, a machine learning course. We got like 80, which is for a master student, it's master class, it's a lot, okay? So really everybody took it basically, and that tells something, I think. Also, all the statistics we have available from industry in Ireland, they want that. They totally push for data science courses, and so if you want to integrate your tool kit, this is a good place to start, in my opinion. Okay. Still communication is there, okay, so but you can add something. Okay, so what is the problem to solution space? So the problem, of course, is finding out how to serve some use cases, how to cope with some scenarios, and the solution space is not necessarily to do with that. It can be more horizontal, so you can have general techniques that could be applied, in different ways to the different scenarios. So you do have things like dense networks that have been there, so over deploying in a sense, so that you get closer and closer to the user. Device to device, ultra reliable, we talked about basically all of them. There are a few things you can do in terms of technology. You can focus on the radio link, so pushing the bits per second per hertz in a sense. MIMO, for example. You can have multi-node, multi-antenna. Multi-node can be also coordination between nodes, interference alignment, and interference cancellation, coordinated scheduling, multi-rat, multi-layer. So you can have multi-rat is something like when you integrate it, for example, with Wi-Fi. Multi-layer is like when you have big and small cells together. So this data control split I talked about yesterday, okay, for example, spectrum, well, cognitive radio and the likes. Now, there are some new things we're going to talk about in this course. So cognitive radio per se is not really on the agenda anymore. It's not practical. What has happened is like a scaled down version of it starts to be adopted by standards in both Europe and US at least. And they are called authorized shared access, licensed shared access. So where it's something in between licensed and unlicensed. So cognitive radio as traditionally put in the scientific literature is like unlicensed. You kind of sneak in, try not to disturb the license holder. The picture in the 5G spectrum sharing story is different. So you are, the incumbent, the guy that owns the license is totally aware you're there. You strike a deal with him, and you can use it as far as you don't breach the agreement. And these are short-term licenses, but once you get the license, you are kind of safe from interference, and there's some variance to the concept, but that's the idea. So the fact is, cognitive radio didn't really fly, except for some limited applications, because the operators are very skeptical of something that doesn't guarantee quality of service. They cannot afford to lose their reputation in their business because they don't provide a reliable service. So to just get extra spectrum without any guarantee, it's a good spectrum free of interference is of no avail to them. They want something they can trust. So this is kind of midway, and it's more flexible than the usual brick wall licensing. Okay, so it's kind of meeting, let's say, halfway between the traditional cellular licensing and the cognitive radio. Okay, again, another hint, personal opinion. You can argue and disagree, of course. My feeling is that cognitive radio is done and dusted the way it used to be. I don't think it's a good idea to start to work now on sensing, stuff like that. I think that, yes?
But we can use cognitive radio, at least the share spectrum we can use it in.
No, yes, yeah.
In wake-up signals at least.
No, we can use some parts of it. What I'm saying is like the traditional story of primary, secondary, relying only on sensing is not really there. It's not practical. So I think there are things like where you have a more flexible way to handle the license, okay? So you don't have just primary and secondary. So primary is holding the license, secondary is sneaking in, that's gone. I think another thing that's gone is sensing alone. Now, definitely with all of this AI, and you have database in the picture, okay? So, yes, call it as you want, I think, but the traditional picture of cognitive radio papers is not really there, okay? That's at least my feeling. And I think there are other topics that are on the agenda now. Now, spectrum is still important because still the most useful portion of the spectrum is where a lot of things coexist. And the interference might be there because of the longer range of propagation. On the other hand, there are new actors, new kids on the block. So you do have millimeter wave, terahertz, Wi-Fi, and the picture there changes radically in the sense that I don't think spectrum sharing could be as relevant there, because essentially it's enough that you are inside the room to completely shield anybody else from your transmission, for example. Definitely if you have Wi-Fi, most likely if you have millimeter wave, terahertz, stuff like that. So you see, it's not that we have such a we have to come up with such a complicated resource allocation at the system level anymore. I remember a big professor from KTH, Ian Zander, maybe some of you heard about him, and he was of the opinion, like we spoke with him a few years ago, forget about spectrum sharing in these new bands, there is no need of it. Okay, so again, open for debate. I think might be not so black or white, but you see, a lot of the things we are worried about in lower frequencies might not be the important thing to focus on at higher frequencies. I think predicting the channel, you know, reliability, circuitry, RF, these are probably more challenging and important at higher frequencies. That's totally my feeling. Okay, so radio engineering is not that; it's just being shifted to higher frequencies. Okay, good. Again, I don't hold any absolute truth, so you might disagree, and you know, and I'm not saying that what you did is, if you're doing work on cognitive radio, it's not relevant. Of course, there is even a journal, right? A transaction of IEEE on cognitive, so TCCN, transaction on cognitive communication, and TCCN, transaction on cognitive communication and networking. It's a very good journal of IEEE. It's been there for a few years, and yeah, they publish these things. Okay, I have myself like some work there, so it's just I'm saying that you have to kind of keep up the pace with the evolution. So I think you have to kind of adapt the concept of cognitive networks to the current landscape. And I think things like self-organization have been there for a while, but still relevant. So you see that they are all part of this idea of making the network aware of changes and possibly fast in responding to them, and self-adaptive, right? So you don't have a central genie controlling everything. It's probably not feasible with a lot of so many sensors, so many cells. So I think it's just that the cognitive radio is changing shape, but yeah, I think it's still there. Not in the usual, you know, old school way though. So depending on the goal in terms of the parameter we want to optimize, there are different technological efforts. So if it's latency, for example, we are working on shortening the time transmission interval, or having new coding, for example. New multiplexing, I mainly mean full duplexing here. I have a lecture on that. Full duplex means you can have, actually full duplex is a bit misguiding, because in the past, full duplex meant you could speak with somebody without waiting for the other person to be done. And half duplex was, you know, kind of the, it's called walkie-talkie, right? Like what you use, like, yeah, when you are a kid and so on. Not just a kid, I mean, probably rescue teams and so on. So but now full duplex, we mean actually something else. We mean you can transmit at the same time and same frequency. So normally what you have to do is you have to duplex your signal in downlink and uplink in time or frequency. Full duplex gets rid of that, and you can do both. Now that has potentially the implication to double the throughput instantaneously, right? But you have other problems like self-interference. So when you transmit, this becomes interference to your own receiver, which is not a problem we have with half duplex techniques. And at system level, you start to have a whole lot of new interference sources. Okay, so for example, in the past, if I'm transmitting in uplink, the only source of interference are other mobile phones, right? Because the receiver is the base station, so there could be interfering signals, yeah? But now with full duplex, it can be actually, yeah, it's the phones, but it could also be other base stations, yes? And it could also be the base station itself, right? Because you have a receiver that could capture your own signal, which is not intended to be, yeah? So there is a lot of interference, and people are working on interference cancellation techniques, so and also at the system level, we have some studies on that I'm going to talk about. Okay, other things like to increase the, let's say for example, the usual thing about spectral efficiency are normally pushing on the phi side, so MIMO, stuff like that. Capacity, density, for example, well, higher bands, that's one option. For higher bands though, you have to be careful because you need very directional communication, because the attenuation is so strong that you need to be very focused when you transmit. So there is the necessity to be having very precise pencil beam like beamforming. Okay. Yeah. Okay. So anyways, you can check. This is more of a general overview. One thing that has been there for a while is like going from link to system efficiency. Okay, so in the past it was all about maximizing the capacity of a link, right? And we were happy with that. Nowadays we can't just afford that, okay? So you do have to keep in mind that eventually what you do at the link level has implications at the system level, and more so nowadays because you have a lot of different communication transmitters in the same area. Okay, in the past maybe, with just macro cellular systems, it wasn't so important probably, okay? You could just schedule your users, they would not interfere with each other because you can control everything, and you have maybe orthogonal multiplexing, right, to transmit to them. Base stations are kind of far apart, so fine. Nowadays you can't do that, okay, because you have actually coexistence with other systems, even Wi-Fi. You have a lot of sensors, you have small cells, and so on and so forth. So you do have to keep in mind that what you do has a repercussion on other links, and to have a system level view. Okay, not so straightforward, by the way, to do this mapping even in simulations. What I found with my team, I mean, there is a lot of work to be done. Okay, when you map link to system, and in general, the more precise you want to be about link, the slower you become about simulating the network. So you can only simulate small networks if you want to be very precise about the link physical layer parameters. If you abstract things, and maybe you just use the Shannon equation based on signal to noise ratio, you can simulate maybe a large network, but then it becomes not a very fair representation of the network itself. So you see there is a trade-off, and the whole mapping between link and system is not a straightforward exercise. It's not maybe fundamental research, but it's very important. So there's like a clear engineering channel. For example, how do you average your signal to noise ratio? Over what bandwidth, over what area, right? Because you have to give a number to the system level, for example, resource allocation module to take its decisions. So you need to represent the channel state information. So there are some tools available out there. We did a bit of work in my team about this. I think it is actually a relevant problem, okay, especially nowadays with a completely different arrangement of nodes, and so how you map actually physical layer to system level is still very relevant, okay. Okay, so architecture, we went through a bit yesterday about 4G. 5G, honestly, we are discussing this in my team. I don't think the dust has settled yet. There is still no real agreement on what the 5G architecture will be. It seems to me one thing that is happening, virtualization is there. So they're trying to virtualize functions to make it more software-like, more flexible. So you might have actually things like mobility management entity that is now distributed. Okay, this kind of things could happen. They do have work on NFV, I think they call it, and SDN. I'm not going to cover much of this in this course, but it's a big part of the 5G story. Okay. And again, if you want to know more, I know people that are expert in that in Dublin, so I can get in touch with them. It's definitely a big part of the story. So how you distribute the functions essentially, and ideally you would like to get them as close as possible to where they are needed. So this kind of resonates with what we discussed about caching, right? It's not just data, you can also cache a function, right? Now think about computing as being in the picture, right? So I don't necessarily have to cache a movie. It could be I'm caching an operation, like for example, I don't know, I'm just thinking like maybe it's about estimating the channel information, okay, and you might actually have that functionality distributed, and then you kind of collect the measurements, you get the overall picture. So think broader than communication. Communication is kind of underlying everything, but I think another area where I feel there is a lot of work to do, and it's very relevant, there's been a lot of work on caching. There starts to be work on caching and communication. I still think computing is a bit not fully integrated, so I think anything that brings computing into the picture and computing, caching, and communication together is something that we have to do. So I think that's another good area for work. You'd need, though, an expert from the side of computing, because honestly, as a communication engineer, it's not that we have much of a clue. We normally come up always with the average example, which is as dull as you can get. I think you can have much more intricate models of computing, right? So I think you need a computing person, okay, for that. There are very, very good works actually, you know, coming up on this part of the story. Yeah. Okay, just this is not exhaustive, I think, but it gives some idea of the things that are happening. So you see some things are already there in LTE, so 4G, and then other things have come up during the year. So definitely you do have even things that honestly I thought wouldn't be touched anymore, like coding. Now you have polar codes, you have, you know, new things happening there. Higher frequency bands, as high as you want at the moment. So definitely I heard about projects on terahertz 5 years ago. Okay, so I suppose state of the art is kind of mature. By the way, terahertz doesn't just mean things for the normal way of communicating. The people working on molecular communication, they consider it as a valid alternative to the biological communication. So one way is basically using molecules and maybe using bacteria, kind of modifying something to convey information, but essentially piggybacking nature. Another example is artificial nano machines that use terahertz communication. Okay, and now sometimes people are a bit skeptical about that because it might be hazardous for health, right, to use radio communication inside the body, but it's one approach, okay, and it suits nicely the scales you're talking about, okay, which are very short. Self-backhauling is something that's coming up. So self-backhauling simply means that you don't have a wired backhaul, but you use radio to do both access and backhaul. For example, you could have a relay. I have some work with Nokia on that, which I don't think is again part of this course. So you do have a relay, and it can use some bandwidth to communicate with the phone, and some other bandwidth to communicate with the base station. Okay, and now, you know, one thing we'll probably do is to go into drones. Okay, because again, you could have relays moving around. Yeah. Okay. Yeah, very big list, so I'm not going to spend too much time on this, but you know, you see here, you kind of see how many things are happening, which are really a lot. Waveform, we'll have quite a bit on that, and also a paper club, so I'm not going to spend too much time. Same with MIMO, we'll have a few lectures on the paper club, but it keeps on happening. Now, one comment, again, personal. I did a lot of work on waveforms with some people in my team. I think you can do very good work still. One thing, though, we have to be aware of what it means to change the waveform. It means you have to change literally every radio of every device. Now, guess what? The operators don't like that. They do not want to change that. So what has happened in the transition from 4G to the beginning of 5G, they essentially use OFDM with filters, because it's the minimum amount of changes you have to do, okay? And that's something that kind of struck me, honestly, because I thought, you know, it would have been more radical, but they do not want radical things. It's called LTE after all. It's evolution of long-term evolution, right? So the problem with that, for example, why massive MIMO was much more adopted is because it doesn't need to change the phones. It can work well with one antenna on the phone. You just need to upgrade the base stations. And in a country like Ireland, which is small, just to give you an idea of the order of magnitude, we have possibly what? something like 10,000 base stations, but we do have millions of users, so it's already what, two, possibly three orders of magnitude difference, right? So it's a big investment if you have to, and you know, people wouldn't like it, right, to buy a new phone just because. So you can't say, okay, I'm releasing 5G, but you have to change your phone necessarily, right? What is that? I mean, I think you have to be a bit careful about that. Other things, yeah, protocol aspects are there. I think HARQ was kind of, again, another topic I thought was settled, but with critical IoT and the low latency, you might have to become more inventive about that, because you can't use the time dimension as much. If you want to play with delay, with latency, no way you can afford retransmissions over time. So maybe the goal there is to use frequency. It doesn't eat uptime, or maybe you have to use space. Again, proactive caching, following the user, learning the patterns is maybe the way to go. So I think signal processing as a way, at least in my head, signal processing is probably going to be very much of the essence at higher frequencies. I think you have to do work there, hybrid beamforming, you know, and new circuits for terahertz, whatever. I think in my opinion, at the lower frequencies, probably more the game about system level optimization and the role AI proactive actions can take, especially if you have to comply with a very tight delay over a long distance. No way you can rely on signal processing for that, because even signal processing, if you come up with a very smart signal processing, is going to be slow. It's going to be very power inefficient if you have IoT. So there has to be, you know, other solutions which are more of a system level nature, in my opinion. Okay. Yeah, so millimeter wave is about using higher frequencies, at least an order of magnitude higher carrier. People are claiming you can actually achieve, so when they talk about this 50 gigabit per second in 5G, they really mean these frequencies. So it's about 50 times faster data rates targeted. Part of the reason, actually the main reason, is because you have a very large bandwidth available. Okay, so the channel capacity can go up quite a lot. You still have some issues, though. You have to be careful to overdo with bandwidth, because it goes into the noise component. Yeah, we are not noise free in the end, so it could be at some point so much bandwidth that, you know, it's really, even the amount of energy you collect might create problems to your circuitry. I'm not an RF guy, but what I understand, it's difficult. Okay, even to process so many samples is difficult, right? RF chains, you cannot, okay, maybe one thing is like the antenna spacing goes with half of the wavelength. Okay, so what does it mean? It means that at frequencies that are normally used for cellular communication, you possibly have to space the antennas about 10 centimeters at least. Okay, this can go down to millimeter, maybe centimeter for millimeter wave. Okay, which is fine, but again, every antenna has to have an RF component, which is costly, it's power inefficient, and so on and so forth. You have to design it, and that's why they're coming up with hybrid solutions, where you have, you know, only a limited amount of RF chains. Okay, so it's in progress. I think, you know, it's not free lunch anyway. And I spoke with people; they're very skeptical about these massive arrays at millimeter wave anyway. They say it's very, very difficult to design them. So as a communication theorist, if you talk with a communication theorist, they would be all very optimistic about it, but if you talk with a radio engineer, much less. Okay, so truth is probably in between. I'm going to talk quite a lot about massive MIMO later, so I'm not going to spend too much time, but you can do MIMO essentially better in any sense, okay, because you have many more degrees of freedom, can cancel interference, cancel noise, become very directive, very power efficient, very high throughput. So it's like MIMO plus plus in a sense, okay? But we're going to talk way more about it. Beamforming is an important aspect, especially at millimeter wave, because you have to become very directive. You might actually have to be not just directive, but also dynamic, because the channel at millimeter wave is a very fluctuating nature, okay? You have things that play a role, like what we call microdiversity, which means I just change a bit the position of my phone, I turn my back to the access point, stuff like that, which now wouldn't have any impact. In a millimeter wave system, they would. So for example, there are experiments showing that if I face the access point with my phone using millimeter wave, all is fine. If I turn my back, suddenly signal gone. It's kind of a binary channel if you want, okay? And the higher the carrier, the more you get impacted by Doppler. So there are, you know, some things that make it definitely challenging. Modulation, again, we are going quite a bit through that later on, so I'm not going to spend too much, but the idea is like you actually move from an idea of having possibly no filter at all to filtering maybe per subcarrier, which gives you quite some flexibility in terms of the design. Another thing is like you have to trade orthogonality with how much it takes to do synchronization. So for example, FDM is very good if you can synchronize things because you guarantee the different channels are exactly orthogonal. The problem is all of this synchronization has a cost, right, in terms of signaling, overhead, and it might not even be feasible if you have a very dense network. If you have a lot of sensors, a lot of phones, at some point you can't do it, okay? So maybe you have to give up orthogonality, and that's one thing. Another thing is like one thing that is not good about FDM is that it uses essentially no filter, which means like a rectangle in time as a shaping, and that implies that you have a sink in frequency which has a very slow decay. It goes like 1 over f, right, which is slow. This is not good enough, especially if you have a lot of systems that are using contiguous bandwidths, because they are all going to see the out of band emission of the other system. So they came up with these non-orthogonal techniques that have another kind of shaping, okay, which is probably more it's like smoother in time, which means again you tend to become very contained in frequency. So you see, if you are contained in time, you are kind of, you know, slowly decaying in frequency, and vice versa. So if you are very if you are kind of, you know, smooth in time, you become very contained in frequency. So again, no perfect solution. I have the feeling about these new modulation techniques, the same feeling I have about the Aloha technique I told about yesterday. So I think it depends on the scenario. So if you are going toward a scenario that is very complex with a lot of devices, a lot of transmitters, I think you have to give up on the precision of synchronization of the access, and you might have to go for something quick and dirty, so to speak. Okay, maybe Aloha and something not fully synchronized is the way to go if you have you know, a network with a lot of devices. But if you have a network like the ones we have nowadays with a few devices in a certain area, then you can actually have something synchronized and you know, scheduling based. So it's both are relevant for the new applications. I think I'm going to stop here for now, and then we continue in the afternoon. So there is an half an hour break now, and then I'll be available from 10:30 for 45 minutes if you want to discuss anything. Okay. Lecture number 4. So I'm going to finish up a bit about the component technologies, and then we're going to start to go deeper, okay, into some subjects that are pertinent to 5G. And today I'm going to talk about MIMO, okay, mostly. Okay, a little bit more about the waveforms. I already kind of discussed the idea of different filters. So you are becoming more selective in the way you filter the subcarriers, and that gives you the benefit of reduced out of band emission, which is good for many different reasons: decreased interference and better coexistence of systems mainly. Okay. You do have actually other things, like for example, kind of combinations of CDMA and FDMA. This non-orthogonal multiple access, it's being proposed. Of course, space division multiple access was there also in 4G, so you have this new kind of new access schemes. Another thing is definitely densification, right? You start to have many base stations per unit of area. And actually people are also going away from the concept of cell per se. So you have actually people talking about virtual cells. So you have, it has more to do with the user experience than a kind of rigid definition of cell.
So you might actually have different boundaries of cells depending on the user quality you want to achieve. It could be, for example, one way we already got away from the original idea of a cell in a cellular system is COM, coordinated multipoint, where you have transmitters belonging to different cells, they all serve the same user. So it's kind of turning, again, interference into an allied, if you want. You have interference alignment scheme. So this concept of one cell versus the rest of the world is already kind of not there anymore. Okay. Duplexing schemes, definitely work is going on there. I think there are still some challenges to solve, but there's been a lot of work on full duplex, okay, and also basically more flexible duplex, you don't have to stick with TDD or FDD. You might alternate. Definitely you can have things like variable ratios between downlink and uplink. For example, if you have one duplexer that has to serve both IoT and broadband traffic, it's likely that you have to change the downlink to uplink ratio, because in uplink is more biased toward, in IoT is more biased toward uplink, yeah, and in broadband the other way around. So if you have one, duplexing scheme set in stone, it's not going to work, right? So people are working on this, and of course there are a lot of implications at system level. As I said before, full duplex means you have a much nastier interference situation, so that possibly, counteracts the benefits, right? So I'm going back to the duplexing later in this course. D2D, similar in nature to, at least in the rationale to small cells. You want to get closer, transmitter and receiver. You have to be careful not to interfere with the communication going on between base station and mobile phone, because D2D is essentially device to device, right? So you have to actually, for example, some work we did was to propose something like you reuse the spectrum of the cellular system, but you use underlay communication, okay? And in general, the power of these devices would not disturb too much the base station, because they are close and the power is not that high, okay? So in case, for example, you want to do file sharing, so caching doesn't have to be necessarily at the infrastructure level, it can also be at the user level. So we have some work. Again, I couldn't fit everything in this course. I welcome you though to check my website, and there might be some works of interest to you that are not covered in this course. We do have some work on caching and D2D. Interworking with Wi-Fi, as we discussed already before, is not as before, where they were considered independent networks. Now they're pretty much, considered to be integrated. At least that's the goal. And you could have even physical integration, sharing. What Professor Das was saying before, doesn't have to be only spectrum. It can be infrastructure, right? Instead of, if you're a Wi-Fi operator and a cellular operator, why do you have to buy two masts? Maybe you can use one and share the location, right? Especially because you are likely going to use different frequencies. So even if you are physically attached, you are going to be anyway orthogonal because of the frequency, right? So these things are also happening. I'm not going to cover again much of this. There are better qualified people, but it's a big part of the story, the virtualization. Okay, so definitely a 5G trademark. Software-defined networks have been there, also the kind of the evolution of 4G. So essentially what you're trying to do with, I think with software-defined network is basically to decouple the control, okay, part from the data part, I think, and they are trying also, they use open flow software, so they are going to make more flexible the operation of the core network. The same thing is, and that's kind of there. I'm not an expert, so I'm not going deeper into that, but the same kind of philosophy is being actually considered for the radio access network. So you might actually have the concept of a slice. So you might have, say a slice could be, for example, an arrangement of resources that suits a particular usage. That's especially important for 5G because you have very many different services that have to use the same network. So you might have an arrangement of resources that targets low latency and another arrangement that targets high throughput. And they are the same resources. The illusion is given to the user that these are not bound. because you get as much as you want. They play with statistical multiplexing. Not everybody will need the same resources all the time, right? Sharing is part of the story. So making the functions virtual and software based. So it's kind of, in a sense, both SDN and NFV are taking cognitive radio to another level. Softwareization throughout the panel, throughout the board, okay? And there is a lot of work going on. One problem, a small problem I have, actually I was also examining a PhD thesis recently. I think there is good work. One issue I have, we are trying to tackle that with some people in my lab, is actually seems to me sometimes when you want to be too abstract, too general, you are actually going to lose precision. So I didn't find, honestly, a very satisfactory definition of virtual function or slice so far. It's at a very abstract level. There are good papers, but I didn't find, for example, a very mathematical definition. I didn't find a very, and it's difficult to do good engineering without that. So I think there is a lot of potential, but there has to be a better effort in terms of formalism. So we are trying, for example, to do some work. Possibly next time I give a GYAN course, I might have some work on that. But I think it's something that has to be considered. So again, for new PhD students, or if you want to find new research avenues, you might want to look into network function virtualization, radio access, network slicing. We have a communication magazine under review. So we have some stuff, you know, it's part of the discussion actually. But it's not really something we cover in this course. So what is the future? Well, as we said, it's not really going to be a revolution as it looks like. It's going to be an evolution, complementing with other technologies that weren't there in 4G, like massive, you know, IoT, critical IoT. D2D was and wasn't there, you know, so these things are coming up. Higher frequencies definitely wasn't there in 4G. Massive MIMO wasn't there in 4G. Ultra dense networks wasn't there. So what was there in 4G was a heterogeneous network. So you had some small cells helping to cover, right, some areas that are not covered by the macro, but that's it. Now, when we talk about dense and especially ultra dense networks, it's a situation which is very different because you have more base stations than users, possibly many more. What does it mean? It means that before the problem was to use the scarce resource, which was the access point, to serve many users. So the expensive bit was the resources and the infrastructure on the network side. Yeah. Now, if you reverse the picture and you have many more base stations than users, it's the other way around. The expensive resource, so to speak, is the user. And you have an array of possible serving points, and you have to schedule the one that makes more sense. So all of the work we did on resource allocation might have to be recast in terms of this new story. So actually the ultra-dense networks is more, in my opinion, than just densifying the thing. We are going back to that in the course, but there are issues definitely to do with performance limits. You can't just over deploy and forget about interference, and channel model is an issue. But there is also the resource allocation bit, which has been targeted much less. So that's another topic, in my opinion, worth investigating. So how you change the MAC and the resource allocation for ultra-dense networks, because the picture is way different, okay? You do allocate the scarce resource, which is the user now, and you kind of reverse the problem. So in the past, it was much more of a broadcast problem, if you want, okay, or multicast. So you have one point, taking decision and allocating resources, right? In this case, it seems to me more possibly of a medium access control channel. Anyway, so or maybe let's say a reverse broadcast. So the user is the one, you know, that has to be mapped with multiple serving points and resources. Okay, so it's very different than what we are used to. Okay, just a picture telling about the network deployment. Okay, so basically you see that there are two things. So there is so there are these yellow and green bars. They're about LTE and LTE Advanced. So you do have essentially, you know, the newer version of the standard takes some time, right, to be adopted, and we are still not there yet with LTE Advanced. So the proper 4G, say, and 5G. Worse still, right? So basically, it would take some time to get it actually deployed. The standard is just being finalized now, so I think essentially it will take some time before we see these networks. And a lot of time before these overcome 4G, okay, in terms of adoption. The fact that you start to have a rollout of a network doesn't mean it becomes the dominant one, right? Because there is inertia, right? Investments and user fidelization, so you don't just get all the users moving to 5G, right? What they mean here, I think, by fully 5G mainly is the usage of millimeter wave capabilities. So that's kind of less mature in terms of technology. There's still work to do. So I think that's the main discriminant here, whether you use sub 6 gigahertz only or also millimeter wave. So I think to see millimeter wave operational networks will take quite a few years actually. You know, research might be there at some point, but you know, you still need a lot of work in terms of deployment. Any question about this part? Okay, so I'm going to move on to so there are some works. Now that's not required to be read for the course. I tried to, you know, put works of mine, so at least, you know, I have something to say in case you have questions instead of picking on works of other authors. Of course, this is not exhaustive. There are many people working on these topics, and you know, this is just a suggestion. So this is a paper we published recently. It's actually it's being well received by community. It's being well cited, so apparently it's useful. So if you want to have a quick, let's say, look without diving too deep into math and technicalities, I think the first paper is probably not bad. Okay, so it gives you some general ideas about what 5G is and how you have, you know, you might want to tailor your radio access technology to suit some purposes in terms of the different services like low latency, high throughput, and we do talk a bit about this virtualization and slicing and so on. Okay, so yeah. Okay, good. Yeah, this student is working on a project I'm doing with Nokia. Okay, and he was behind some of this material, and yeah, Professor Das already said it, but I'm basically a senior researcher of the Irish National Telecom Research Centre. It's like a research center that spans across the nation. The headquarters are in Trinity College, Dublin, but we do have other 9 institutions affiliated. It's like a federation, and we do have quite a few companies working with us. We are talking in the order of probably 250 researchers nationwide. Okay, so it's kind of a large center, and we span many different topics, not just the ones I cover in this course. So you might want to check out the Connect Research Center website, okay, in Ireland to see what we do. Okay, so now we start to go more into business. Okay, so far it's been warming up. It's like in the movies, right? In the beginning nothing happens, and then you wonder why you're there at all. But then suddenly there is a twist and turn of events, so that's what will happen now, hopefully. So we are going to see actually PHY and latest trends for a few days. So I think, if I'm not wrong, this is going to be until Friday. So we are going to see quite a few things, okay? In terms of PHY, again, not exhaustive, but I think I give you a flavor, okay, of some of the important trends, hopefully. So I have to start first from the basic, though. We can't talk about advanced MIMO if you don't know basic MIMO, right? And maybe it's going to be insultingly easy for many of you, but still feel it's not a bad idea to refresh the basics. And by the way, if you read or are going to read the Marchetti paper, as you should, by today, you see that it takes that approach, right? Marchetti is considered to be the inventor of massive MIMO, or one of the pioneers, and he literally starts from the very basic, right? So point to point, then it goes multi-user, and then it tells you why you need massive MIMO, what's different about it, right? Because many things we could already do with simple MIMO, right? So why do we need massive MIMO even? So I think he explains that. So basically there are a few goals you want to accomplish with the MIMO scheme. MIMO simply means multiple input, multiple output. It's not a terminology that is unique to wireless, right? I'm pretty sure in control you have the same thing, and other, right? Whenever you have inputs and outputs concerned, and you have a transfer function in between them, you could use MIMO terminology, right? You could literally have something that has nothing to do with communication, right? But in our context, what we really mean it's a wireless. You could even have MIMO on optical side, fiber side, but we are talking about wireless here. So you have multiple antennas at the access point or base station, and in the case of normal MIMO, you would assume at least 2 antennas at the mobile phone. Okay, so you have multiple antennas there too. Essentially, there are 3 families of techniques that you can play with. Spatial diversity, which is about making the channel more reliable. Essentially, it's like repeating the information you transmit over multiple antennas and sending the same information, basically. Okay, more or less. What's the trick? If you make sure that the different antennas see an uncorrelated channel, then you're good to go, because in case one channel fails, likely the others won't. These techniques don't work if you have correlation between the channels the antennas see, because then if one fails, the other fail too. This is true, by the way, for any diversity scheme, right? Same with time, same with frequency. Diversity is about redundancy in a sense, like what coding has been doing for a while, right? Channel coding. So you repeat information. Most basic example of channel coding is repetition coding. You just do that using time, right? But if you have a huge correlation between the slots in time, frequency, or space, of course, if one fails, the other will fail too. So the underlying assumption is that you have to have a correlation between the paths, okay, the channels. So that's diversity, okay. Multiplexing is the other way around. You send different information over the different channels, again, exploiting independence or uncorrelation of the channels, so that to maximize the rate. You don't care so much if you fail something, as much as you care about the raw throughput you can transmit. Okay, multiplexing is the other extreme. Beamforming is different altogether, because diversity multiplexing can work even without channel state information. Of course, they would do a better job with channel state information, but they can work without. Beamforming cannot. Beamforming is about using the channel information to kind of pre-code what you want to transmit, so that to achieve some goal. For example, being very directional toward the user you intend to transmit to, and being basically transmitting zeros, nulls, toward the users you don't want to interfere with. You can create a radiation pattern changing the weights on the antennas, right, which are essentially based on the channel you estimate, and that is something you can do with beamforming. Now, this is something that's covered in Marchetti paper. What was done in 4G is actually they basically have a code book. They have a set of pre-coding matrices that kind of work fine on average, and they basically pick between them. But in essence, they don't look at the actual channel. They just have some, options which are normally few, like few, really 3, 4, and they kind of select them as transmission modes. But you can do way better than that, and ideally, the best thing you could do, if you want really to be super precise, you could actually use zero forcing. So you could essentially invert the channel and multiply, right? So, and that's the best thing you can do, because what you receive in the end, I mean, you're like transmitting h to the -1 times x, right? The channel inverse times the transmitted vector of symbols, and once you receive the thing, you also again pre-multiply everything by h, which is the actual channel. So what you have now is h -1 x. H times the inverse of h is the identity, so you get exactly what you intended to transmit. That's the best thing you can do. Okay, there is noise enhancement, so now it's getting complicated, but you can do like you can take care of the noise enhancement with MMSE. Okay, and then there are even more advanced things that rely on information theory, like dirty paper coding. Dirty paper coding essentially tells you that if you know where the interference is, just by avoiding it, you can maximize the capacity. Okay, it's like you have a stain of ink on a sheet of paper. If you write anywhere else, that's the best thing you can do, right? Instead of writing on the ink, of course. So there are a lot of things going on, but a lot of this conversation happened when I was in my PhD, so we go back more than 10 years. So, MIMO has been there for a while, and way before that, because I think the first fundamental papers on MIMO for wireless, we are talking mid-90s. Alamuti paper is 98. VBLAST spatial multiplexing at Bell Labs, probably 96. I'm collaborating with a professor in Greece who is in the, actually was part of the team that built the first MIMO prototype in Bell Labs. He's one of the pioneers really of the field. And they're still actually, doing good work over there. Okay, so essentially, depending on what you want to achieve, you will pick a different technique. For example, if you're targeting users that are far from the base station, it's much more about reliability. It's much more about being precise when you send information and energy efficient, both ways, uplink and downlink. Therefore, spatial diversity and beamforming are mostly meant for this kind of users. They're kind of far, they don't see a very good channel, okay? Multiplexing is more for users that see a good channel, so they are normally closer to the base station, yes? So you actually can be cockier if you want. You send your information without much protection because the physics will help you. You're close anyway, right? If you're sending to the cell edge, then you have to be more careful. You can't just send whatever rubbish comes to your mind. You have to make sure that information will go through. That's where you start with coding, right? You don't need, by the way, channel coding if you are sure you're never going to have a mistake in the channel. You need channel coding when the channel introduces mistakes. You don't need to use low modulation orders like BPSK if the channel is great. So all of these are part of this concept of adaptive link transmission, right? So MIMO is just one of them, is one example. Power control, right? These are all things you can play with to make sure that you reach the target, which is, mostly connectivity provision at the cell edge and high throughput at the, close to the cell center. You also have in between, right? So you have hybrid schemes for intermediate regions of the cells, okay? So now, a part of the story is why is MIMO so successful? Because actually it does something that is akin to other techniques that were very successful, and it's essentially playing like fiddling with the Shannon capacity. Okay, so you actually have two ways to do it using MIMO. So you can either increase the factor that multiplies the logarithm of 1 plus SNR, because you can actually prove that under some conditions the capacity gain you get from MIMO is equal to the minimum between the number of transmit and receive antennas. To simplify, if you have the same number of antennas, say it's four antennas at the transmitter, 4 at the receiver, you can show actually the capacity goes up by 4 times. Okay. But you might say, okay, what if I get 4 times the spectrum? Well, you can do that, right? But what's the problem? First of all, it's not spectrally efficient because you are using a lot of bandwidth. Right, and so that might not be always possible to have new spectrum anyway. So one of the main reasons behind MIMO was to actually avoid using more spectrum. And just with the spectrum you're given, become more spectrally efficient and boost the throughput that way. Okay, so you're boosting the throughput, but at the same time you're boosting the spectral efficiency. Techniques like cognitive radio and spectrum sharing, they don't do that. They boost the throughput, but they also penalize the spectral efficiency, right? That's not what MIMO is about. Any question, comment? Feel free to ask, okay? So again, what is MIMO? There are a few flavors. So point-to-point means you have one physical transmitter, one receiver, and they normally have more than one antennas. Now, whether that's true in current phones, I wouldn't swear on that, because the last time I checked, it was not even clear phones had really 2 antennas. There has been a lot of boasting about MIMO and so on, but in fact, one of the reasons massive MIMO was successful is that it doesn't require more antennas at the mobile phone, right? So I think still now state of the art is a bit dodgy about that. Okay, I'm not too sure how much multi-antenna is going on at the mobile phone, honestly. Last time I checked, I wasn't too impressed. Okay. And multi-user MIMO is about this. You actually can have a virtual MIMO scheme, but without the need to have more antennas at the mobile phone. So you just kind of consider this as a holistic thing, as a network. So you would have, in this case, for example, on the right-hand side, 3 antennas, a virtual array of 3 antennas. It's just that physically they are not in the same place. Okay. That's why this lecture is called co-located MIMO. It means that all the antennas are in the same place. Okay, so we are thinking of more about things like a mobile phone with multiple antennas, a base station with multiple antennas. 4G and 5G have changed a bit the story because they started to consider things like coordinated multipoint, multi-user MIMO, right? More coordinated multipoint is considering virtual array, a virtual array on the transmitter side in the downlink. So you have base stations with one antenna maybe that kind of form a coalition and they form a virtual multi-antenna array. Multi-user MIMO is the other way around. You have actually the users that have one antenna and you kind of consider them together and you kind of form a virtual array on the transmission side in uplink, okay? So largely speaking, the theory is similar with some differences. So the coordination is complicated, synchronization is not so straightforward because things are not in the same place. You might actually get more complicated RF because you have, for example, local oscillators are not correlated anymore, right? They are actually, it's a hardware problem also, and I think though there are some advantages. Mainly, if you want channels to be uncorrelated, that's good because they are going to be. If they are in different positions, most likely they are more uncorrelated than if they are very close to each other, right? So that's a benefit if you want to provide actual independence of the channels. Yeah? Now, I'm aware I'm using interchangeably uncorrelation and independence. Strictly speaking, is not so true because independence is a stronger requirement. But let's say, for our sake, they're equivalent. Okay. If I was teaching my information theory course, I wouldn't do that. Okay, so it's a general purpose course, so I'm a bit more relaxed. So yeah, so basically you can use multi-antenna for different things. As I said, capacity, coverage, range. Very important, for example, the role of diversity if you have things like sensors. If it's about increasing coverage, if it's about being more energy efficient, more reliable, that's probably what you want in IoT. On the other hand, if you have enhanced mobile broadband, just to put it in the context of 5G, you probably want to go for multiplexing-like techniques. You want to boost, right, the data rate. Okay. Yeah. So, and then you have, of course, other things like beamforming could be good for localization. Okay, you could actually use angle of arrival, right, estimation techniques to estimate the position of something. Interestingly enough, location has been one of those topics that have always been there, but they never really made such a big splash, as far as I can see. It's there, okay, I think, and it could be that now with the integration with satellite networks, maybe they become more relevant. I think there has always been a good amount of work, but it's never been one of those topics, that made highlights, right, the news. Even if you see any presentation on 5G, you might have a word or two about that, but no more than that. And again, could just be that we don't have yet the right application. We are happy enough with what GPS gives, maybe, I don't know, to some extent. So MIMO works best if the environment is rich. Generally speaking, you can again show that the capacity you achieve in a MIMO channel has to do with how many scatterers are there. So scatterers, I mean anything that kind of diffracts or scatters the signal. And why is that? It's similar to what they do with CDMA rake receiver, right? You use the multipath to your advantage. So it's kind of, in a sense, redundancy again, right? You are kind of incrementing the amount of information you receive, right? If you are able to compensate for the phase, right, of what you receive and the amplitude, basically you can constructively sum things. It's like adding information, right? Similar to what they do with chase combining. So these ideas are there, okay, and MIMO is also using them. And in general, the more such sources of multipath you have in your environment, the higher is the capacity. Now that's a bit counterintuitive because we would think that a cluttered environment is actually bad for wireless communication. We would think intuitively that. MIMO is counterintuitive in that because, again, if you do the proper signal processing, this is good. because you get replicas of the signal. You don't just get the line of sight, you get many others, and that can boost the capacity quite a lot. I mean, you can show that theoretically, okay? Massive MIMO is the same, okay, same story. Yeah, a bit more on space diversity. So you could have situations, for example, where you have multiple, paths. So, for example, if you have, you can have it also at the receiver side. So, in this case, the mobile phone has one antenna, but the receiver side has two. So, likely the two antennas, if they are again spaced far apart enough far apart, they would see a different channel. What does it mean? That if the blue, let's say, signal fades, maybe the red signal won't, right? And it has to do with multipath reflections and also with angular spread. So the more open is your an array of antennas, the more it can pick, right, multipath. So there is a relation between the angular spread and the amount of capacity you can get in this case, or benefit, okay, if you talk about diversity. So it has to do with space variability in a sense. So there is this concept of space coherence, right? So it's like coherence time, coherence bandwidth, you can have coherence space too. So it's about reliability, diversity. It's not just about space though. You can do similar things in frequency and time. In fact, channel coding, as I said, is basically diversity in time. Think of repetition code. That's exactly what you do. You can do the same thing if you have a multi-carrier system. Okay, you could, for example, assuming that you are beyond the coherence bandwidth, you could replicate the information to achieve redundancy, right? So if two different frequency channels are spaced apart more than the coherence bandwidth, it means that if one of these channels fades, likely the other won't, because they are uncorrelated again. So same story, you just change the physical knob in a sense, but the intended effect is exactly the same. Okay, for space diversity, time diversity, and frequency diversity. It's pretty much what I already said, so I don't think I have to say much more about the domains. It's just a bit more clear probably. So you don't have an infinite amount of things you can do, of course. Anything we do is bound by degrees of freedom of an engineering nature. So what can you do? Well, you can push diversity as much as this product. So you can play with the number of transmit or receive antennas. You can actually play with the number of paths, or you can play with essentially the rank of the time correlation matrix, okay, to be a bit more formal. And for example, if you are boosting the number of antennas, you're going to get higher diversity. What does it mean, diversity, by the way? It means if you plot the bit error rate versus SNR, you are going to get a steeper curve the more this product number increases. This number will reflect in a steeper curve, okay? The higher this number, this product and T and R, KL, the more you will push your bit error rate curve to the left. What does it mean? Energy efficiency, right? You need less power to achieve the same level of error, right? Performance. Now, some things you can really control, some things are much more difficult to control. So definitely antennas you can control to some extent if you have the hardware capability, the real estate space, right? I mean, these things for base station and so on. That's why, for example, millimeter wave is a popular topic in combination with MIMO, because you have the possibility to squeeze more antennas, right, to some extent. Now, L and K is a bit different, the story, because it has to do with the environment, okay? So can you really change the number of delay paths? As it stands, not really, but things might change. For example, drones could do that, right? You could have a drone going up to clear the path. You could also have a drone going down to increase the multipath, maybe, if you want that, right? That's the degree of freedom you don't have nowadays. And you can play with frequency. If you go high up in frequency, you are going to see less multipaths. Millimeter wave, definitely very little. If you go down, again, so you might think of an adaptive scheme changing actually literally the the frequency diversity order. It's not something we have right now, I think. But you know, since it's so important to have this number to be high, that's the design parameter you might have, okay, in future systems. I'm not sure about time, you know, dimension, because it has essentially to do with the mobility of the environment. Okay, the faster you move, the lower is the coherence bandwidth normally. And it has to do with Doppler spread, basically. Okay, so but again, if you go to millimeter wave, you are more sensitive to Doppler spread and mobility. So you know, that impacts anyway the diversity order. The problem is if you go high with the, I'm thinking if you go high with the correlation index, I'm not too sure how it pan out. So probably you would have to, if you become more diverse in time, it could be a problem, because if you start to have two mobile systems, that's not so easy to handle, right? And you have feedback problems, so I'm not sure you can harvest all of this diversity, okay? But this is just to give a general picture. What can you do in terms of multi-antenna diversity, okay? Essentially what you can do, you see, if I want to transmit a symbol X, whatever, you know, QAM symbol or BPSK symbol, PSK, whatever you want, you actually multiply that guy by a different coefficient over the different antennas. It goes through the channel. You do multiply what you receive at the receive array by another set of coefficients, and the problem here is an optimization problem. Essentially, you have to pick these alpha parameters and these beta parameters such that you optimize the signal-to-noise ratio. Okay, for example, you can show that schemes like Alamuti plus maximum ratio combining at the receiver are optimal in this sense. Now, they are not general. They don't work if you have more than 2 antennas at the transmitter, for example. Okay, so you have to give up something in terms of optimality if you go higher with the number of antennas. Okay, but essentially, so what you are doing basically there is something like, I'm just trying to keep it simple. So you are basically playing with some, you are kind of conjugating your signal, and then, you know, you are playing with both time and space. So you are creating like a transmit signal such that when it goes through the channel, it gives maximum SNR. That's what Alamuti technique did. Again, very smart technique. The guy is now a big manager in Intel, I think. He published in '98, immensely influential paper, very easy to understand, very simple idea, but kind of, you know, very, very good. And it's been going in the standards everywhere. If you look at the idea and you are used to be to signal processing, you will see what I'm talking about. It's super easy, okay? But again, very smart idea. Yeah, now one thing I want to stress is the impact of channel knowledge, okay? A good thing about diversity techniques is that they do not necessarily need the channel knowledge, and they are therefore useful for environments where you have high mobility. Why? Because in that case, it's probably difficult to get a actual estimate of the channel that is up to date, right? Because the channel changes quite fast. So it probably is of no use to send feedback, okay? So that's why, for example, it also made it in standards, Alamuti technique, this space diversity techniques, because they do not need really channel state information. So they go well with lack of channel availability. Now, if you do have channel availability, of course you should use it. So I don't think these guys would do a good job. Even in terms of reliability, it's probably better to do beamforming. But for that, you need channel information. So you see, it depends mostly on what speed the system is moving on. Now, you might think of speed just in terms of the user. It's not bound to be the case forever, because now with, again, drones, you do have mobility also on the base station side, possibly. So that could lead to a lot more variability, right? And a lot more of coherence time reduction, possibly, to the point that I'm not sure if you can really reuse the current feedback-based systems. Okay, so maybe again the story of anticipating the moves with AI might be something relevant here. Okay. Multiplexing, the story is different because you send the same information, different information over each antenna, and you can have different versions of it, something that doesn't need channel state information, something that uses it, okay, and of course you get better performance if you can do that. Essentially the story here is that you turn your MIMO channel into a set of parallel SISO channels, so single input, single output, and basically it has to do with the eigenvalues of the singular value decomposition, and you could combine these, for example, with water filling, with power, right? If you have a better eigenvalue, higher eigenvalue, you could put more power there. If the goal is maximizing throughput, right? If you also have to keep an eye on fairness, you have to be careful doing that, because you might want to give more power to the weaker channels, possibly, right? Depends on the goal you're after, okay? The good thing is that the gain is of the capacity is it goes with the minimum of the number of transmit and receive antennas, so it's definitely a linear boost. Same thing as with spectrum, but with the advantage of not using more spectrum, so being spectrally efficient, right? So spectrum is good if you can get it, but if you can't, then MIMO is a good way out, yes, to boost the throughput. Any question? I think it's fairly basic so far, so probably, yes. Yeah.
In a MIMO, we started with the assumption of a highly uncorrelated.
Yes, if you have diversity multiplexing, beamforming is different.
So shall I understand that for a MIMO to be giving those diversity gains, we need to have a environment with a more number of multipaths, as you explained
Yes.
in one of the slides.
I think that's beneficial, yes.
So if we talk about the rural scenario, not a dense urban scenario, then does MIMO help to that extent?
I think probably less. Okay, so I suppose you need some kind of clutter.
Because diversity gains will only come to play
Yes,
when we have a uncorrelated.
I think you're right. You could do other things though. If the goal is to be reliable and power efficient, you can still do beamforming, right? And for that, actually, beamforming works the other way around. It needs the channels to be correlated. So you see, for that, you don't need really multipath. You could have a way out with beamforming. I think you're right though. I mean, you do need to play with. You do need to have a good environment in terms of scattering and multipath reflections. Now, interestingly, one thing people are working on, some people at least, is to create artificial scatterers, especially when you have things like millimeter wave, where you might have. It's more like removal of obstacles in that case, right? You might have to move panels, or maybe create artificial scatterers to boost the situation, because a millimeter wave is kind of poor in terms of multipath, right? And you might still benefit a bit if you have it. So they are thinking of panels that move around, smart materials, so literally creating the environment you want, okay? So it's more like, if you want, it's not really transmitter and receiver engineering, it's more of environment engineering, yes? Transfer function engineering. You can do that. I mean, I think there are some works in this space. Now, in the rural area, I'm not sure if you have the budget or the possibility, but if you, for example, could place some few, you don't need probably too many, right? But if you could come up within a certain area with 4 or 5 scatterers, better than nothing, right? So you could, for example, do that, but you would have to design, right, the channel you want, in a sense. Yeah.
Does the 5G technology envisages in a scenario where there is less of a multipath and all those things, there the beamforming comes into play? Yes. I think that's gains which we are not able to get from the MIMO.
I think so. I think beamforming could be a way out. In fact, I mean, already because of other reasons, millimeter wave is all about beamforming, right? So I think it's definitely a way to go. As a matter of fact, I didn't hear too much about diversity techniques in 5G. Okay, it's also because the conversation is all about very smart techniques that rely on the channel knowledge, right, and a lot of information. So I didn't hear too much. Still, I feel for things like very fast environments, it could still be that diversity plays a role, huh? Because in that case, I can't see how you can get channel feedback reliably. So So it could be for very fast communications, there is still a point to do diversity, okay? And in that case, for example, you could have, for example, one antenna at the receiver on a fast train, say, or on a plane, and then as long as you make sure that your antennas are like spaced far apart, it might still work fine, especially at the ground level, I think. The big advantage is that you don't need channel feedback, but there is the question about independence of channels. So one part is like the antennas being spaced apart, so it's like the source, right? But also it has to be different the path they follow, right? Because let's say you are independent at the source, but then at some point you get completely coupled. That's not what you want, right? So I think the scattering environments still kind of need to be there. So I'm not sure this would work even in fast mobility in the rural environments. Probably you still need to go for beamforming in that case, I guess. Yeah, my guess. Okay, another question?
Yes, I have a question.
Yes.
So actually, literatures are saying that hybrid combining techniques, like maximal switch and stay combining technique, provides better diversity gain than maximal ratio combining techniques.
Yes.
So is there any constraint, particular constraint to increase the diversity gain by using this hybrid combining technique?
So hybrid combining, what do you mean by that exactly? So is it?
Yeah, that is maximal switch and stay. So
Okay.
that is hybrid combining.
Okay, I'm not aware actually of this specific technique. I think you can probably play a bit with that. I think in terms of hybrid, what I heard is also on the transmitter side. So you can actually combine techniques. I did some work myself during the PhD, so you can combine space diversity and spatial multiplexing. You get a bit of both. There is actually a work from Tse. It's kind of traditional fundamental paper. I think I have a slide on that. They study the trade-off between diversity and multiplexing. So you can actually, do some tweaks. If you really want to be best at everything, you should do maximum likelihood. The problem is complexity, right? It takes a lot of time. So I think traditionally MRC is not a bad solution. There are probably, I'm not fully up to speed with the current developments in terms of MIMO receivers, and I suppose you're right. I mean, there are maybe other things you can do. I think in general, theoretically, the best thing is maximum likelihood, though. It's non-linear, very complex, so that's the problem there, right? Yeah. Okay. Yes.
The rural situation that Suvra was talking about, would it apply if the user equipment is on a skyscraper?
Yes.
That is also a post-scattering environment.
I agree. Yes, I think in that case, I'm not sure you're better off doing beamforming. I think multiplexing and diversity rely on this rich scattering. That's what they mean by having independent channels, really. Okay. If you can't have that in a desert, open space, in outer space, these situations, clear line of sight, that's really meant to be beamforming, I think. Okay. So you have a clear target. You kind of focus all your power in that direction, and that's the best thing you can do. Okay. You see, in a sense, what they did with multiplexing and diversity was to get the best out of a nasty situation. The same they did with CDMA, with the rake receiver, same story. So you are kind of using something that is potentially bad to become good. You see, even interference, if you make it constructive, is good, right? Because it's kind of superimposing the signal. You have again chase combining in terms of packet, right? Retransmission. So this concept is there, okay? To use something that maybe has gone badly or not fully okay, and you do some work. Essentially, you have to align amplitude and phase, and then you're just boosting things. You actually see a nice example of that with Alamuti, where they show that if you do Alamuti and MRC, you actually literally get a boost of the SNR, which is equal to the number of links. So every new link adds. So in the normal situation, this would all be interferers, but they all go and boost your SNR because of the processing you do. Yeah. But that requires independence. If you don't have independence of channels, I suppose the only thing you can do is some beamforming. Yeah. But that's good enough if you can do that. Now the problem is if you do not have, I think if you have, maybe that's a bit theoretical, if you start to have things like a user moving fast and no scattering, then it starts to be very complicated also for beamforming because you can't acquire the channel state. So these are a bit theoretical. Now, one scenario I was a bit puzzled by, I heard it from Nokia. So when you have drones, I think I mentioned it yesterday, when you start to have all of these drones flying around, you have a situation which is about weird multipaths, if you want, because you have all line of sight paths. One is yours, and the others are interference, so a lot of interference, but they are not like weird things. They are all kind of, you know, straight lines. And then, but these things move around, so you have a very different situation in terms of scattering. It's not even scattering, it's multipath, okay? So I think multipath is also a consequence of the topology you assume, okay? Of the speed you assume, because you could have something that is way more intricate, way simpler. With drones, right, if you move up, no multipath. If you move down, full of multipath. It has to do with the frequency. Down, a lot of multipath. Up in frequency, very little multipath. So you see, it's kind of, it depends also. It's, in a sense, my feeling, I'm not sure how much work there is on that. It's totally possible to conceive it as a design parameter. If you want to have multipath, you might create it yourself. I was talking about these moving panels, right, artificial scattering. So far it's been mostly, the channel has been mostly something you are given. You optimize something based on the channel, right? What if you change the channel though? The drones are about that, by the way, even though they don't say it probably explicitly. Yeah, so you can actually think, not just to optimize transmitter and receiver, what if you change the channel itself? It might make sense, right? So maybe you are not doomed by the multipath you have. Maybe you can change that, okay? Yeah. It's a bit futuristic, I think. You know, I'm not sure we are there, probably not for a while, but think along those lines, okay? So it's the same story about the ultra-dense networks. It's not written in stone that you have to have more users than access points, right? Actually, ultra-dense networks reverse the picture. Same, normally, what we think is like, okay, we are given a channel, good luck with that. You do the best you can, right? But maybe not, okay? Maybe once you understand the channel well, and you understand what you want to get out of the channel, then it becomes itself a knob you can tune. Why not, right? It's a transfer function you can modify maybe. Of course, some situations are easier than others, but it's totally possible to think about that. Okay. Any other question? No? Okay, so multiplexing, again, it's about sending a lot of information simultaneously, uncorrelation again required. The receiver has to have, normally, unless you do something fancy like parallel interference cancellation, things like that, you need at least as many receive antennas as transmit. That also was a bit of a bummer for cellular communication because it means that to really harvest the multiplexing gain, you need quite a few antennas at the receiver, right? That was one of the reasons why MIMO didn't really fly, and massive MIMO does a better job because it doesn't need that assumption of multi-antennas, yeah? So, but to have multiplexing, you need this, you have this constraint essentially. So if you have 4 antennas at your access point, you need at least 4 antennas at the mobile phone, okay? You can do a few things. Normally, the communication systems are symmetric. You do somehow, the block diagrams are, let's put it like that. So you have something going on at the transmitter, you inverse that, you revert that at the receiver, pretty much, right? It's a mirror, right? You start to have, where you have ADC, you have DAC. Where you have coding, you have decoding. Where you have modulation, the modulation, and blah, 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 right? Fine, but normally it's more difficult to receive. That's the whole point of telecommunication, right? If it was so easy, you wouldn't have degrees and everything, right? So it's difficult. So it's not so straightforward to understand what they sent you, right? So the less effort you put at the transmitter, then the more you have to pay off at the receiver. So the multiplexing is very easy. You literally send, multiple streams, nothing to do literally in terms of coding, but then the work is on the shoulders of the receiver, right? So you see, and again, bad for downlink because this guy doesn't like that, right? Good for uplink probably, yeah. But again, for uplink you would need multi-antenna. So I think the story of MIMO has been, even though I worked on it for a while, it still gives me mixed feelings. I think massive MIMO, in my opinion, is a better deal because it has the same advantage as not changing the waveform. You don't have to mess up with the mobile phones. Massive MIMO is good for that. Yeah, MIMO has the same problem as all the work I did myself on multiple waveforms. You are going to change the radio transceiver of the mobile phone, which is bad. Okay, cannot be good. So MIMO has a similar issue with it. I see it more as a progenitor, okay, like a pioneer, and then many more fancy things came. We are going to see about that. I think MIMO per se, unless you are really, probably if Wi-Fi situations are still, or like when you have a tablet, okay, where you have more static situations where you can afford to have a lot of antennas in one place. So collocated MIMO has still a point. Network-wise, much less so in my opinion. Okay. In fact, you did have multi-user MIMO, COM, massive MIMO because of this. I'm saying right now. Yeah, just to show that it goes up linearly with the amount of antennas, right? So of course that's a good thing. It's a big advantage of MIMO, and that's why people were so keen, because you're going from maybe something like say not even 10 bits per second per hertz. You go to maybe 35, just by adding few antennas, right? So that's very good, actually. That's probably the main selling point of MIMO. There was this paper I mentioned before. Actually, if you want to read it, it's a nice read. It's information theory, but again, not one of those that are impossible to understand. I think this is not a bad paper, actually, to read. So these guys, they characterize the trade-off between diversity and multiplexing gain. So you have the multiplexing gain on the x-axis, and you have diversity, which is a function of the multiplexing gain on the y-axis, and it's a trade-off. You can't achieve both at the maximum level. So if you want to go for maximum spatial multiplexing gain, which is the minimum of NT and NR, you are going to get 0 diversity gain. If you want to get the maximum diversity gain, which in the case of space diversity is given by NT and R, you're going to get 0 spatial multiplexing, and then all in between. It's like a Pareto thing, right? A Pareto frontier. And you actually have it more of a knob to tune between different environments. You could think of it, for example, if you are serving users that are close to you as a base station, you should go for the lower end of the trade-off. As soon as you move away from the base station as a user, you should get served with some points in the middle, and at the minute you are at the edge in trouble, then you should go with the upper point. Yeah. So you see that actually this makes sense as a design knob, right, to serve different regions of users. And in fact, myself and other people, we did design techniques in the past few years, keeping in mind the different regions of a cell. Okay, so you do have there has been also good work done by the professor in Korea. I think Suvra remembers him. Chai, yeah, and then Is also in US. So they have actually a nice paper about adaptive MIMO. So where they show, for example, the condition number of the MIMO channel matrix tells you what to do, right? So whether you should go for multiplexing or diversity. So this whole idea about adaptivity at some point came in, and it kind of added to what we already did with adaptive modulation and coding, okay? Adaptive power control. MIMO was just another thing we added to the mix. And by the way, this all laid the ground for cognitive radio. Because see, cognitive radio is about choosing between options in a smart way, but you have to have options in the first place. If not, you can't choose. Same with the numerology about LTE, about 5G. You want to be flexible to serve fast tight delay and maybe high throughput users, but you have to have some degrees of freedom, right? You cannot choose if you're not given the options. Yeah. So first you have to provide. Well, I think the adaptivity story goes like that. First you have to have a need. So my opinion would be, first you have to study whether there is a chance and a point to adapt. If you have an environment that is very static, forget about adaptation, right? So you have to identify in your mind the regions where you should move, right? It's kind of the states of your system. Only after you do that, then you start to think what could be the options, and then you start to design flexibility into the system. And then you get learning, intelligence. But I think the first step, which people sometimes forget, you have to see whether there is a point at all. Okay? Because in some environments, maybe you are just better off with one set of parameters and techniques, right? Okay. Now, adaptive antennas, it's been forming. So essentially you are, I mean, there is a set of benefits traditionally, so increase the range. You might want to reduce co-channel interference because you get more directive, right, with your beams. Yeah, so basically let me think, the decrease in access delay. So essentially what you do, okay, so multipass is a double-edged sword, okay? It's good for what we said before, diversity, but it can also be bad in the sense that it leads to higher delay, right? You start to have copies of the signal that are going to mess up with the current one, right? Intersymbol interference. That's due to multipath, essentially, right? So that could also be bad. So the good thing about beamforming is that it gets rid of this because it becomes very narrow, the beam, very focused. You don't have multipath in the end, so very little impact of intersymbol interference. So maybe you don't have to become smart in signal processing in terms of intersymbol interference cancellation because you already do the job at the transmitter, okay? And it's a new way to provide access. If you provide orthogonal beams to different users, it's yet another way to provide multiple access. So it goes on top of time and frequency. So you could use the same time and frequency slot as long as you separate your users in space. Yes, which is a good thing. So it increases the capacity of the network. Yeah, I'm not sure I'm saying too much. It's just a visual representation. Of course, you can have single and multi-user systems. You have to align beams, no big deal, usually. Big deal if you're in millimeter wave though, because of the variability. You know, the environment is very sensitive to any small change. So there, it starts to be a complication to have beam alignment between transmitter and receiver. It goes also with the problem called user tracking in millimeter wave. So you do have to keep track of your users. The problem is, you know, if you have a millimeter wave, also the propagation range is reduced. It's similar to what you have with dense networks. So it means that you have to follow the users through many handovers. So you have to realign beams all the time, right? And in millimeter wave, it's also to do with, you see, you have to be very precise. So even if the user doesn't change cell, it just moves in a circle around the base. You have to keep on tracking that, right? So you see, again, it gives flexibility, but it's also a complicated technique to implement, especially in high frequencies. Okay, so there are issues there. Yeah, this is not really saying too much. It's just you know, a schematic representation. So essentially, what you do, you come up with a set of weights that are based on the channel you estimate, or some code book you already know, and then you pre-multiply your transmit vectors by these weights, and this has the consequence of becoming more or less directive depending on what you do. Okay, so in the ideal situation, you become very directive, and you can place nulls toward possible users you might interfere with, and that hits two birds with one stone, because on the one hand you get a better throughput on your side, on the other hand you reduce the interference for the system, right? So system throughput will go up by this, and energy efficiency also, right? Because you don't squander your energy in useless directions. You just put all your energy where it's needed. Okay, I think I gave a fair picture of MIMO, at least what I could do in 1 hour. We are going tomorrow. We are going to discuss other, let's say the more 5G story with distributed MIMO and massive MIMO. Okay, and we'll also have the paper club on massive MIMO tomorrow. So we are going to go deeper into this. Yeah.